you have any question? Want to talk?
Do we have DLC class, DLC duty today?
I don't think so.
No?
No.
Okay.
Yeah.
It's finished?
It's finished.
Okay. Good.
How about this final exam? I mean, this mathematics physics last?
Yeah.
Last week.
Physics.
You feel good?
Oh, well, I mean, I was struggling
At
on
least
it.
comfortable, right?
There was a question on there asking for the proof of Cauchy residue theorem,
Yeah.
and I swear I looked at everything else but that right before it, so.
Uh, that is open text.
Yeah.
So you mean couldn't find any information from textbook?
Oh, no.
That
Those-
is closed book.
Yeah,
Close.
Book, yeah.
Wow.
That's closed. Yeah.
but like, we like practice so much,
Uh-huh.
material before, but.
Uh,
I have solved around 80 points. I
Okay.
cannot make to solve the 100 points.
Oh.
Okay.
The question number 3 residue theorem, that's second and third question, I could not make it.
Oh, the two integrals? Or what?
Yeah, integrals.
Yeah, no, those were bad.
I have done perfect one, and the rest of two is, I don't know what I had. Right, very tough.
So you did one of the integrals perfectly, but the other two?
Yeah.
Yeah, that's how I feel about it.
Yeah.
Which one did you do perfectly on? Was it the first one?
Yeah, first one.
Yeah, no, that's, yeah. Yeah, no, and the other two? No.
Yeah. So I think in the test 3, I will score around 80. 80 points.
I think I'm at least in the 70s.
That's okay, so you pass, right?
Yeah. It should have gone a lot better,
So
but
how about this, even for the special integral, no any provided the equation sheet, you have to remind everything.
Yeah.
yeah.
That's a good thing.
Yeah, well, remembering is,
Yeah, I remember, yeah.
either, you've worked out all the, different kinds of residues and,
Yeah.
you know how to approach it, then, but, yeah. There's no memorizing when it comes to those integrals.
Does the exam cover Laplacian
Yeah.
equation?
Yeah.
Yeah.
So you have to remember all of them?
Oh, so, no, she gave like a table for like the
Oh.
Laplacian transforms. But like, to like derive, like the Laplacian of a second order derivative, you gotta be able to, show how you get that. Yeah, those are all good. All the Fourier transform series, those were perfect. But when it came to those two integrals from the Cauchy residue ones, why?
Yeah. Let's first go to the exam, right? See if you have any question on this. So first one, if you the general force QR, try to find the potential general potential U as R and R dot. You can do.
Yeah.
Okay. If not, then the remaining part is just follow, right? Lagrange equation, write down the Lagrangian and follow Lagrange equation and discuss the equation motion and what kind.
Right.
So I think that is not difficult. How about second one? How about, the first one is okay, right? Okay.
This was my-
Uh-huh. We have this pendulum, but this suspension also move on a circle. So that is a little bit additional degree of freedom, right? So the first issue you need to find the right. Of course, it's really depend on different person, different test, case, which kind of general coordinates you're going to select. Someone maybe select angles, or maybe select some others. So you need first think about the degree of freedom, how many, independent degree of freedom, then you are going to select. If you miss one of them, you probably cannot go over, right? So
This is exactly exercise 20, chapter 8.
Yes,
Exercise 20.
yes, that is, yes. Okay, no question about the 2, right? Problem 2. Then the problem 3, I think, just do it, right?
Just for the question package.
Yeah,
I
that-
have already done in the 1 dimension.
one dimension, yeah, so there's 2 dimension and you have a series. Yeah, so I think C here is not so difficult. You can move on. I know after tomorrow, who has, you both also has this statistic?
No,
Data.
no.
Okay, so you're fine.
Yeah.
You have time. When you prepare tomorrow, and on Thursday we will have it in class. Yeah. So I think that is okay. Any other question? If not, let me just discuss some of simple examples about this, how to apply the Hamilton-Jacobi equation. We play, I think, 1-dimension harmonic oscillator in the class, right? So I feel this is important, and this is really the way how to solve this mechanical problem. So let's play one more, and let's do this. Remember, we said that if it's a separable, so we can have this. Let's consider separate, right? This, right? For example, we have 3D harmonic oscillator. Remember, if you find you have some question not related to this one, just stop me and we can discuss it. Okay, so Hamiltonian, we know that is half, this is a kinetic energy half m and px squared plus in Cartesian, right? In Cartesian. I'm going to define both cases, Cartesian and spherical, how to separate. Kinetic energy part and potential, which is this. Suppose we have the omega x squared. I think if you remember quantum mechanics last class, right, we also have these examples. Which, and it's a topic harmonic oscillator in 3D. So the frequency is different. Okay. So immediately we can see this can be written in or separated into 3 parts, x, y, z, right? Okay. Or we just say this, use I, right? I and I from x, y, they go 1 to 3. And each one, so now we are going to use this general coordinate, that is p I squared plus p I squared I plus half of m omega I squared I and qi. That's good. Then this one for 1D, right? So we already have the 1D, then we can go to this together. Let me use that's the example, right? For how to separate. Then I'm going to take one example in spherical. Spherical coordinates. Okay, so Hamiltonian, in this case, we use r theta phi, right? So the angular momentum will be, remember that is p r squared plus p psi squared over r squared, and the potential is function r. This is okay. In this case, is the anisotropic. Now here we consider as isotropic. So isotropic, then this the friction, the same. The Hamiltonian react this way. Okay, this one, if you we also learned quantum mechanics, angular momentum in chapter 5, right? That is that part, of course, this part, and then so I just use this one, and I will not go to the details since we will not solve this one, but to just give you an idea, the Hamiltonian can write this way. So you can see this R, this one, this R, this is a side, right? So how to separate? Okay, because partial Hamiltonian partial T is 0, right? So we know this Hamilton-Jacobi equation is reduced to H equal to alpha 1, right? So let me say the alpha 1 here. Okay, so over, yeah, let's say alpha 1. So now, then what we have to do, let's first substitute, right? So that means half of this PR squared plus P psi squared over R squared plus VR equal to alpha 1, right? Then I'm going to, because this constant, I'm going to make all the R dependent in one side and the angle phi dependent on the other side, so we can separate. How to do that? We multiply R squared both sides, so this becomes independent of R, right? So there's R squared. R squared. PR squared plus VR minus alpha 1 equal to minus P 2M R squared P phi. I just move this term to the right hand side. Then I'm going to multiply this R squared both sides, so I have R squared plus all the R squared together, right? So let's just do this one. R squared, and inside is this R squared plus R minus alpha 1 equal to minus P psi squared to M. So this one is left hand side only depend on angle, right hand side only depend on R. So if they are equal, this will also give another constant. Alpha R, right? So then we can separate. Then you can see here you have two equations: R squared P R squared over 2N plus VR minus alpha 1 equal to alpha R minus P psi squared over 2M equal to alpha R. Right. So now we can separate. Since this constant, so this equation is only for R part. This one only for angle part. Then this Hamilton-Jacobi equation became two parts. Then the remaining part we have to find this which type of this geometry function. F1 type, F2 type, F3 type, and then you are either replace this one or replace this one. So the remaining part, let me see if I. Okay. Let me just here. Because the first part issue is easy, right? So now let's, if we deal with this one, right? So now I have this one. Okay. So in this case, if it's like F2, it's F2 type, right? So in this case, this is F2 type is function of R. I use R, right? R and theta, I think. Is all angular momentum. Mu is alpha P, right? So that is, okay, alpha R, alpha theta. In general, is this one. So this one is a capital P. This one is QG, right? Something like this. So that is this, and because here, I just give you some of the details about this one, equal to 0. So S is equal to this, the only this time dependent part is, let me see, I have several, okay. I use alpha R, right? This alpha R here. So alpha 1, yes, I use alpha 1, right? Here. So there are 3 alpha, so this is alpha 1 minus alpha 1, right? T. And plus the characterized function. And characterized function now, since we can separate R part and theta part, sorry, phi part, so that is this one. Then if we select F2, so we know the PR is the old one, right? Old conjugate momentum is partial S, partial R, right? Remember, for F2, PG is partial F2, partial QG, and capital QG is partial F2, partial capital PG, which is partial F2, partial alpha G. So we have this, and now since this does not depend on R, so the only is a partial R. That is a separate here, and then you can also have a P theta. Okay, P theta, partial S, partial theta, right? This is this one. QG, there are 2. One is R and theta. Oh, sorry, I think I use theta or let me sorry, to not make a confusion, I'll use theta. Okay, so P theta is partial S, partial theta, and here this does not depend on theta, partial W theta. So that is, then you can, for example, here, substitute PR here, there's a PR square, right? And this equation and solve this PR, or solve this one. Then substitute this one into here, so that is solve this one. Then when we have this 2, we can come to here, right? So that is, then if we have this, now we go to here. This capital QR, which is be constant, right, beta R, and that's be partial S, partial alpha R. Okay. Partial alpha R. Here, you see. Okay, and then there's another one is beta theta, and it's partial S, partial alpha. Okay, I just give us this one. We will not go to details because that integral is complicated. Just give you some idea. If we use spherical harmonic spherical coordinates, then we use this R theta phi. So how to separate? We still can make it separable, but not like this. This one is real Hamiltonian. So the Hamiltonian separate, and then we can use each I for this, because this also Hamiltonian does not depend on time easily, right? So we solve this one for each x direction, y direction, z direction. So you have solution, and we can combine together. So this one is easier, we already solved this one. But if we use this spherical harmonic here, then you can see here, this is not Hamiltonian R. It's not Hamiltonian, right? Because we have R squared here. So but it's still separate with some time, some terms which equal to constant, so you can separate only R part. This also not Hamiltonian on theta, but this one still can solve as the theta part. Then we just for each one. For this one, starting here, so you can solve this. For this individual, then you can find individual. The remaining part is this diffuse. Okay, I think I want to go to one example which is like this and separable. Then also we can do some of the diffuse, get some idea about this how powerful of the Hamilton-Jacobi equation. Another example is okay, we have a particle moving on vertical. Okay. Vertical plane. Then now let's try to solve this system. Then the fun is try to find this find the dependent coordinate QG, find the solution, right? And the trajectory of this motion of this particle. So here let's consider if this is vertical, let's use xy. Usually we use z, right? But this one also. So any particle here, we have mass. We need first write down the Hamiltonian character, right? Okay, Hamiltonian kinetic energy because it's two dimensions, so px squared plus py squared. Potential. Potential, let's consider, take the v equal to 0, gravitational potential, right, at x-axis, so that is the distance. So that is mg, right? Okay, so that is Hamiltonian. So once we have this, now let's first, we can analyze several things. Let's first analyze this, which type of Jacobi Hamiltonian equation, right? So first we found, okay, the Hamiltonian does not depend on time explicitly. So this equation is, we can use h equal to constant. Okay, now let's use this constant, just energy. Right? We just replace alpha instead. Energy is a parameter or constant. So that is the equation. The first, then we immediately know, so if this case the Hamilton's principal function s is minus, since alpha here, right? Let me use e, right? Okay. Use e t plus characterized function. The characterized function is x, y. Oh, okay, we did, of course, here the I select F2 type, right? For second one, you select. Okay, so the first step, second step, select this. Okay, this first step is, let me just do this. First step, not second step. Second step, select S is S2 type, right? So that's the S is a function of X, Y, and if, let me, since this momentum, right? Momentum is constant, so we use alpha X, alpha Y. Let's see if we use, I really use that one. Okay. Alpha 1, alpha 2, let's just say, since we do the reason why I use alpha 2 is that it may not just the convert to or transfer, canonical transformation transfer to the new space. The new parameter of the conjugate momentum is 2 constant, but they are not conjugate momentum. They may be energy, maybe some others. So I'm going to use constant, right? Just index alpha. So that is the, and since in this one, right? So that is minus EP plus W, which X, Y. Okay. So here, since this alpha 1 actually is this one. One of the parameter, one of the constant, right? So we already used it, that is this one. And then instead of, I just use E and alpha 2. Because we have only 2 constants, and we already know there's one constant here. So I give an index alpha 1, and that is this one. So when we do the partial like this, when we do the one of partial alpha j, so that is one is for this one, right? So that is this case, the first. Now, it is also because the Hamiltonian can be written as x and y, right? Separable. Since x part is only this one, y part py squared plus mty. So the s can be also separate, which is w. Okay. Then use 1, and 1 which is only x, and alpha 2, and plus the second one is only y energy alpha 2. The parameter we do not separate, but only the variables separate. So when you write down here, it's the second step, right? Now we can have this. So step 3. Okay. Now step 3 here, this one, the Hamiltonian equal to E, right? That's it. It became Hamiltonian is half of m p. Oh, okay. So now, like, because I have 2, that's a px, b partial s, partial x, right? Partial f is partial w1, partial x. Only w1 depends on x, right? And py is partial s, partial y. And then here only partial w2. So that's why we can separate. Then, number 3. So now, this Hamilton-Jacobi equations become half of m, right? The px is partial w1, partial x squared plus partial w2, partial y squared mgy equal to E. And we know this is separable, so we can separate 2 equations. Actually, I didn't discuss since do not have time, but here, these 2 equations actually just need to solve one, because here, one more, because here, you see x is cyclic, right? Cyclic, even in the O, here. This Hamiltonian does not depend on x, right? Only px and y, py and y. So the coordinates x is a cyclic. So what does mean? The px is partial I think we just do this. So px is be constant, right? Let me say this way. If this one of the general coordinates is a cyclic of Hamiltonian, because remember, px dot is minus partial x, right? That equal to 0. So we have a px be constant. And that constant, let's introduce is, I'm going to say is alpha 2. Because this is constant, then we convert to this, the new canonical transformation, the new set of canonical variables is constant, and that is partial W1, partial X. Is here. So that means this one is constant. Then now, this equation, we need to solve X and Y, but actually we just solve Y. So here, half m, then this one is alpha 2 squared. And of course, we do not know the alpha 2 we're going to solve, but this W is constant, so we don't need then only the Y. W2 Y squared plus mg Y equal to E. So that is only this one. Okay, and this one, move this one, so that is mathematically we can do that. Move, we have 2m multiplied there and there, right? And in the alpha 2 squared, so that is 2m e minus mg y, and then this term, right? Minus alpha 2 squared. So we have the partial derivative of this one, just square it. 2m e minus mg y minus alpha 2 squared. And that is a function y, so we can do the integral, but we do not need to do the integral here. Okay, that we need s, since s, oh, okay, that is also fine. Let's get, since we need s, we need w, so w is the integral of this 2m e minus mgy minus alpha 2 squared dy. Partial y. And of course, we have some of a constant here. When we do that, we will finally have constant, but we just keep this one. So that is W2. Then we have S. Since now we're with erase, right? Okay, now we have S is minus E T plus W1 plus W2, right? So, what is W1? From here, W1 is alpha 2x, right? If we do the integral. Partial W, partial x equals alpha 2, so the W1 is alpha 2x, right? So we have this plus alpha 2x is W1, and W2 is this integral. Okay. This integral inside, right? Minus mgy minus alpha 2 squared dy. Keep in mind this is P1, right? That is here. This one. So we have Px alpha 2 Py is this. Once we obtain this, is this function, right? So that is already here. Now, this one we are going to capital Q1 is partial S, partial alpha 1, right? By the if we select F2. So then now we have S. Alpha 1 is nothing but this partial E. We select alpha 1 is E. That is here, right? So then that is minus T. Here we have also this one. So that is plus. Then this integral go to denominator 2 m e minus mgy minus alpha 2 squared. And then we have half cancelled, right? So m, that is only m, right? For this term. Okay, this be beta 1. Then if we move, so now we are going to solve this one So then this beta 1 plus t is this interval. And this integral actually, I think now after the mathematical physics, probably very familiar with this. So I'm going to give the result, which is minus 1 over mg square root 2 1 e minus mg1 minus alpha 2 square 0 1. That is beta 1. Okay. From here, our goal is try to find y as function time. That is the question here, right? So that is goal. That like qj is a function of all the other, like this capital Q1, and also the alpha 1, all the other constant, and alpha 2. So here, what we just, since alpha 2, let's see, okay, let's introduce another constant. Since we use this m here, x, we can also use angle, right? Spherical coordinates. Polar coordinates. So here, introduce because the px is a constant, right? Alpha 2, which is the most multiply this x, which is constant. So that's be the initial velocity cosine alpha. So now, if initial velocity, what is the direction? We just project direction to the x components, right? So that is this one. Second one is energy, since it is constant, right? mv squared, that's equal to half of mv naught squared. Okay, so when we are going to, so that here the alpha 2 and the energy will substitute by these two. Then you just give a final, so then the y, okay, still in intermediate style is gt plus beta 1, right? That's equal to, after we substitute into those, we have the, and also we have 2, right? When y equal to y and y equal to 0, so we have 2 terms, and these 2 terms finally is equal to v naught square sine square alpha. This alpha is angle, right? It's not this is not parameter. 2g y and plus v naught sine alpha. So from here we find y, finally y as a function of time, which is g. We'll take a square root. Move this to the left hand side and then make a square root both sides so you can have a y, so have some square here. Finally, y is very easy, and you know that C familiar. V naught, and just goes skip every details. V naught sine alpha t plus beta 1 and minus half of g t plus beta 1 square. And you can see beta 1, that is the initial part, right? Because they have same dimension. So beta 1, of course, when we substitute the initial condition, we can determine beta 1. So that is the time-dependent coordinates from here, right? And the x, where is x? Here. From here, x equal to this one, right? So x, you can also do that. Let me, okay. second one. Let's try to determine this. So t equal to 0, y equal to 0. Then we have, finally we have, that gives us beta 1 is equal to 2 v naught over t, and then we select what is the eject this certain angle, right? And then you get initial velocity, so then the trajectory is like this. Something like this, right? So that is either this one or this depend on initial and then or 0, time equal to 0 or time equal to, I think that is this part. So then the finally you have y. So finally y is exactly this condition down here. From y is v naught sine t minus pi. And that makes sense. This part is because acceleration is the gravitational constant. So that is like this one. Yeah? So, under the action of gravitational force, the trajectory we can easily know, but let's try to prove or try to obtain. This is a time-dependent part, and x is a constant with this one multiplied, right? So that is we know. So we do not need to x. Now from the trajectory, we are going to use this one. Q2 equal to beta 2, right? That's partial s partial alpha 2. S here. We have alpha 2 here, we have alpha 2 here. So we have two terms in this case. So that is equal to the first one, partial x, right? Partial alpha 2, so this is x. The second one is again do this, but now is do this alpha 2 instead of energy. So minus from 0 to y and alpha 2 dy m e minus m gy minus alpha 2 squared. Similar things like this, right? The variable is only this term, y, so we can easily get this solution. That is x plus, I already, okay, let me first put it here, plus alpha 2 m2g 2m e minus mgy minus alpha 2 squared 0 y. Then again, we use this initial condition here, substitute energy and alpha 2. Then finally, x plus v naught cosine alpha g squared v naught squared sine squared alpha minus 2gy minus v naught sine alpha. Now the left hand side is beta 2, right? So then our goal is try to find the relation between between x and y, since this is a set of relation between x and y. So now let's give the finally the just move a little complicated. We have a square root also. So finally we have y is x minus beta 2 tangent alpha minus g x minus beta 2 square 2 v naught square cosine square alpha. This gives us a trajectory between the relation between x and y. Now we do not know the f2, beta 2, right? So we can determine beta 2 using initial condition t equal to 0, x 0 and y 0. So we have beta 2 is equal to either 0, like that one, beta 1 0. Another one is minus 2 v naught square over g cosine alpha. Then we are going to select this one to the equation. So finally, we have y is okay, that is the second first step. Tangent alpha and then g x square over 2v naught square cosine square alpha. And here we have x square and y. Yeah, I think that's enough. Okay, there are two. Either select 0 or another. If you select this one, is another one. Is y equal to x plus 2v naught square g cosine alpha sine alpha 1 by tangent alpha and minus half g x plus 2v naught square cosine alpha sine alpha over g square over v naught square cosine square. And then which is this parabolic. So this example showed this to solve this Hamilton-Jacobi equation. We deal with the first order partial derivative equation, which is integral. So if we're familiar with different type of integral, then it is doable in general. We can solve the problem. And actually finally, you can find, you're familiar with this result since we select the similar system with our classical mechanics. I mean this your order of physics 460, right? That one. Use the Newtonian mechanics, right? So now we use the analytical mechanics. By this way, we do not need to analyze the force. If you use a Newtonian mechanics, you have to think first how many force. Do not miss any force, right? And then you're going to project X components, Y component, Z component, and then each one you have solved. So that is a vector deal with a lot of vectors. And you have to also consider sometimes if I have a constraint. It's not easy to get the force. You know the constraint, right? So the Newtonian mechanics sometimes deal with this complex system. It is not easy. So analytical mechanics get rid of vector analysis. Just consider the scalar, like a potential energy, kinetic energy. If you write down correctly, select this correctly the general coordinates, then we can deal with mathematically, right? Yeah, that is, I would like just give you the idea how this Hamilton-Jacobi equation works. And do you think it is better than this Lagrange? Lagrange, you have solved equation solved the second order differential equation, right? And of course, Hamilton equation first order, but if we have some crossover term, it's a really specific case depend. But in general, here we have a general procedure or step which you can follow, and in principle, it is doable. Of course, deal with if the integral is very complicated, that is another issue. That is, yeah, that is the goal. This class, I just want to have this knowledge about this theoretical mechanics. Actually, to develop the theoretical mechanics, the goal I develop is give this step to the quantum mechanics, statistics, use the idea, right, Hamiltonian and Poisson-Braque, and the way of analysis is more general to the other field instead of mechanics. Yeah. All right. Any other question? You have question with your homework?
No.
No. Okay. How about the Jack?
Not now. Could I
Okay.
email you? What,
Yeah.
I'm trying to formulate it for number 3.
Yeah. I will be in the office, so you can stop by if you any time you have questions. Yeah. So the Thursday, 3 p.m. right here. You will take home exam. You can bring your the material if you want. Maybe can help you. It is also not difficult. I mean, yesterday I say not difficult. Science. I believe you. Yes, I hope. Yeah. I mean, not difficult means you can understand the problem. You know how to do that.
Yeah.
If you do not know how to do that, that is difficult, right? No way how to start it.
So you said one from chapter 10. But,
Yes.
But we didn't cover all of chapter 10, did we?
How chapter 10 kind of.
Did we cover like
Kind of like
10.1, 10.2?
yeah, 10.1, 10.2. Let me see, 10.3 also. Right? 10.2 is the example of this one-dimensional harmonic oscillator. 10.2. Yeah. 10.3 is actually just a separable, right? Characterized function, yeah, W. So that's the idea. When the Hamiltonian does not depend on time explicitly, so the S is equal to minus alpha 1t and plus W. So that's the idea. If you do not use that, you still can keep S. Do not use, but then if you say, okay, I'm not familiar with this W, so use this Hamilton-Jacobi equation in two ways, right? Either. So in this case, most cases depend on time. In this depend on time. If not, is this one, right? So in this case, this is minus alpha t plus. This case, so if you say even here you're not familiar with this, you just use this one. And the key is which type. Depending on which type, so you are going to substitute either the general coordinate or conjugate momentum into the Hamiltonian self-equation. So that is the problem, something like this. You're going to look at the gauge field system, and you're going to look this which type you're going to select. And with that type, you're going to solve this one or this one. And the remaining, right? Find this coordinate strip. The goal is finally you need to find right? That is our goal and and of course, if I write down in detail, it's R J, right? Or beta and also beta J. So you need to use the initial condition, find alpha J and beta J. And finally it's only from beta. And this one, beta J is Qj, right? And alpha J is the PJ, which is I will not say P, depending on which type of S you can select. Textbook give a type F2, but how about the others? That is thinkable. Yeah. Okay. All right. Good. So just stop my office if you have any question you want to talk to me. Thank you. See you on Thursday.
See you.
So in this homework, and we suppose u equal to in one dimension, we suppose u equal to only x, and with in two dimension u equal to xy.
Yeah, there's an X and Y, right?
X and y, and
Yeah.
we need to
You're either
use
equal to
one-
X or Y, right?
Yeah.
Yeah.
We need to use that a p times c.
Yeah, you use that one,
Right.
yeah.
That's fine.
It's fine. Find the expression of
Yeah,
X and Y,
it's
right?
easy.
Yes, yes.
Yeah.
So U, there are two, right? X
Yeah.
and Y, and
Yeah.
then you substitute this G
Yeah.
H here, you do that.
Yeah.
yes.
Okay, yeah. I had the same question. Could you,
Yeah, yeah,
Could you restate that, please?
okay. So you, right, so you either x
Right.
or, so U1, let's say U1, U2, right, is y. And then there's a U, if U naught is x naught, right?
Mhm. Yep, yep.
And plus some sense, this, almost, which one is what? And this is at the initial case, right?
Mhm.
Yeah.
So that must be capital is count.
Yep.
Canonical transformation to new one is a capital, but then equal to when the zero is actually is go to lowercase, right?
Mhm.
So key is here, you do that. Of course, this u is x, right?
Right,
X,
right.
and then that y is y.
So we did it for x, and then we
And then you
did it
do
for
y.
y.
They're
Okay,
separate.
okay, okay,
Yeah.
okay. So they are separate.
Yeah, they are
Right,
separate.
okay,
Yeah.
okay, okay.
Oh, separately then we don't need we don't allow like this one. U equal to x y and this type x y x.
Yeah, sure. Yeah.
Yeah.
X, here the g is become x, right?
Yeah.
So you already did it?
No, yeah, this is the class.
Oh, class, yes,
They
there's a
did
one
the
dimension, right? Yeah. So this case is for one, and
Yeah.
this x you do that.
Yeah. For the two dimension,
Yeah, for
u
two
equal
dimension,
to
yeah.
x y
Yeah,
and in the
Not multiply, not
not
you.
multiplied
Yeah,
separately.
just separate,
U
yeah.
equal to x, u equal to y.
Yeah.
Okay.
Because u is here is
Yeah.
u is always a function, right? In
Yeah.
this case, the function is one of functions y x, another function y. Then since the Hamiltonian, I almost told you the Hamiltonian, we know the parameter is time, right? So then you just do, so you find finally you will find that one. Okay, x plus.
Okay, good.
That
Okay.
is
So we will get the two answers.
Yes.
Okay, good.
That's
That was-
good.
Okay, thank you.
Good.
Thank you. That-
Not
that's-
products.
Yeah.
Yeah, okay. Yeah, I was thinking how I was gonna formulate that. I was like, okay.
No, yeah,
giving-
products is, yeah.
Because like
I have the confusion whether we take the multiply or we take the single.
No,
so
yeah, that's,
that's fine.
yeah. Let's see, did I describe it clearly? So we have the Hamiltonian simplifying in two dimension, and the expression of position x and y, and right, so and not the product.
okay.
Yeah, if you can also let others know if they have questions.
Yeah, no. and that
Separate,
was-
so separate, okay, right?
Yeah.
Yeah.
That was my big one. That was
Right.
that was my okay. I feel much better.
So have confusion.
Yeah.
Yeah.
I know, if you do not understand the question clearly, you cannot easily to start with. But when I say but, actually it's almost so but you need this edge. Edge
Yeah.
has a px, py, right?
Yeah.
Yeah. So that this you cannot only select x.
Yeah.
So you need from this relation, Gaussian bracket between this.
What about for KX as well?
Sorry?
Kx by x. Kx is kx by 2 into x squared.
Say again?
Yeah, that kx.
Oh, yeah.
This is a constant.
That
is
constant, yeah, that
X
is
and Y
constant.
level.
Yeah,
That is
And
constant.
X and Y.
Yeah.
Gotcha.
Yeah.
Yeah. Oh, number one says particle news in a plan. Okay, okay, so that's gonna change the the kinetic energy.
Which one? You mean the field number 3, 4?
No,
The number 1. Yeah. Number 1 you have, you have R. Yeah, you have write down the kinetic energy.
Right.
Yes.
So since it's in a plan, we need to use.
Since we use R, so that is it's a 2-dimension, right? Then you use a polar coordinate instead of x and y.
Okay.
But of course, if you're familiar with, immediately know So that is V square, if it's Vx square plus Vy square in the partition.
Yeah,
right?
yeah, yeah.
If a VR square and then this V theta square, you know the formula, right?
Yeah.
If you know, you direct know. If not, you just start from here and write this one.
Okay.
Relation between x and mass.
Okay.
Yeah.
Conserve. Are they conserved like for each, you know,
So yeah,
if I get thetas or are conserved or?
whatever it is partial Lagrangian partial integral, right?
Yeah,
If this equal, sorry, if this equal to 0, then this is constant, right? That's constant.
yeah.
So that is Calix.
If it's not constant.
Yeah.
Okay.
And
Gotcha.
also ask whether it is I forgot. Second one, Hamiltonian whether it's equal to energy or energy function. So you need to find the condition. Remember we discussed the Hamiltonian when which kind of condition satisfies the equal to energy. In general, it's not. Remember? Chapter 8, you can follow.
I'll look back at it.
Yeah.
Yeah.
He knows. He guided the things. Yeah. We have the examples or discussion on this
Yeah.
class. You can go back to chapter 8.
Yeah.
Go back to the notes.
I will. It's just been one train wreck after another. It's like,
Yeah, I know a lot of.
mathematical, and now I'm
Sure, you have several class and all the information in your mind. You have separate which one is related to this class.
Yeah.
Yeah,
Right?
no,
Yeah.
like class on quantum, like we're on a back burner, like they're in the mathematical, and now quantum's put in a special place right now.
Yeah,
I spent 30 minutes looking at the problem, so they can stir my mind. So after Thursday I can.
You can concentrate on the quantum.
Yes.
Yes, now focus on this theoretical. Yeah, even for me, sometimes I say commutator, but it is a Ponzi bracket. So
Yeah.
sometimes you have to switch.
Because on number 3 also I was like, wait,
Yeah.
what the hell was I doing?
Yeah, Mark looks familiar about this, right? That is why this developed the basic of the quantum mechanics. People use this idea and develop quantum mechanics.
Yeah. Okay, well, thank you.
You're welcome. Good. My goal is you know how to apply your knowledge.
Yeah.
So not just let you make you difficult and give the low grade. That is not my goal.
We're supposed to learn that.
Yeah. Okay, good.
Okay,
See
great.
you on Thursday.
Yeah.
See you.
I'm glad I recorded that.
What?
Oh, okay.